Algebraic Structures, Lecture 12, Problem Session. Problem 1. Find a presentation for the symmetric group S3. Solution. Recall that the group S3 consists of the following 6 elements. We have the identity element, the transposition of 1 and 2, the transposition of 2 and 3, the transposition of 1 and 3, then the 3 cycle which sends 1 to 2, 2 to 3 and 3 to 1, and the 3 cycle which sends 1 to 3, 3 to 2 and 2 to 1. We can compute that doing transposition of 1, 2 after the transposition of 2, 3 gives us the 3 cycle 1 to 3. And doing these two transpositions in the opposite order gives us the 3 cycle 1, 3, 2. Then we can compute that 1, 2 after 2, 3 after 1, 2 is equal to 2, 3 after 1, 2 after 2, 3, and this is equal to the transposition of 1 and 3. So in particular, we can get all the elements of S3 by composing the two transpositions 1, 2 and 2, 3. So S3 is generated by these two transpositions. Let us denote the transposition of 1 and 2 by S, and the transposition of 2 and 3 by T. Now it is clear that these generators, S and T, satisfy the following relations. So first of all, they both are transpositions, so they square to the identity. So S squared is equal to the identity, T squared is equal to the identity, and we also computed that STS is equal to TST. That's the common value of this is a transposition of 1 and 3. Now let us consider the group G, which is given by the following presentation. It has two generators, A and B, and 3 relations. A squared is equal to the identity, B squared is equal to the identity, and ABA is equal to BAB. So we just model what we already know about S and T. So we want to prove that this group G is isomorphic to S3, and in this way we obtain a presentation for S3. How can we prove that? Due to the theorem from our lecture, the universal property of groups given by presentations, there is a unique group homomorphism phi from our group G to S3, which sends A to S and B to T. That's because S and T satisfy the relations which are satisfied in this group G by A and B. And the group G is a universal one for these relations. The homomorphism phi is of course surjective because we already know that S and T generate S3. So in order to prove that phi is an isomorphism, it remains to prove that phi is injective. And to prove that phi is injective, it's enough to estimate that the group G has at most 6 elements. Okay, so how do we estimate that the group G has at most 6 elements? By definition, G is generated by A and B, so which means that any element of G can be written as a word in A, B, A inverse, and B inverse. Since we have the relations that A square is equal to the identity and B square is equal to the identity, we know that A is equal to A inverse and B is equal to B inverse. Therefore, each element of G can be written as a word in letters A and B, and that's it. Since A square is the identity and B square is the identity, there is no need to repeat the letters A and B, so AA and BB can be shortened just to the identity. So any element of G can be written as an alternating word in A and B, so a word of the form AB, AB, and so on, or BA, BA, and so on. Also, the final relation which we have, it gives us that ABA is equal to BAB. And this relation implies that any word of length 4 or longer can be shortened, can be reduced to a shorter word. For example, if we have a word AB, AB, and then some W, we can substitute ABA by B and B to get BA, BBW. Now BB is the identity, so we get BAW. So the original word is equal to the shorter word with less letters than in the original word. And we can do this always if the word has length 4 or more. This means that what remains are the alternating words in A and B of lengths at most 3, and these are E, the word of length 0, A and B, these are words of length 1, AB and BA, these are words of length 2, and we have the word ABA, which we know is equal to BAB, that's a unique word of length 3. So we have at most 6 elements, and we can now claim that G has at most 6 elements. If we only look at this analysis of our words, we do not have that these 6 elements of G are different. However, we can use a different argument to claim that these 6 elements in G are indeed different. So since G has at most 6 elements, and phi is a surjective map to a set with 6 elements, phi must be injective and hence an isomorphism, so it's bijective. And so, since the image consists of 6 elements, the original group must have at least 6 elements, so G has exactly 6 elements. And now we can formulate the answer to our problem. So the group S3 has the following presentation. We have 2 generators, S and T, and 3 relations. S squared is equal to the identity, T squared is equal to the identity, and STS is equal to TST. Problem 2. Let phi be an endomorphism of Z3, whose matrix in the standard basis is the matrix 12, 12, 24, 48, 48, 96, 36, 36, 54. Determine a decomposition of the cokernel of phi into a product of cyclic groups as in the classification theorem for finitely generated abelian groups. Solution. In order to solve the problem, we need to reduce our matrix to a diagonal form using elementary row and column operations, except that we cannot divide by non-invertible integers. It's okay to divide by 1 or minus 1, but that's it. So we start by subtracting 4 times row 1 from row 2 and 3 times row 1 from row 4. The outcome is the matrix 12, 12, 24, 0, 0, 0, 0, 0, minus 18. Now we can change the sign in the last row to make minus 18 into 18. This means we multiply with minus 1, that's allowed. And now we can use the 12 in position 1, 1 to eliminate all other elements in the first row. So we subtract column 1 from column 2 and twice column 1 from column 3. The outcome is a diagonal matrix 12, 0, 0, 0, 0, 0, 0, 0, 18. Having this matrix, we can read off the preliminary answer that the cokernel of psi is isomorphic to z modulo 12z, the first diagonal element, so this is z12. Then z modulo 0z, this the second diagonal element is 0, that's just z. And then times z modulo 18z, so that's z18. Now this is not a decomposition as in the classification theorem because 12 and 18 are not powers of prime numbers. So we further decompose 12 as 3 times 4 powers of prime numbers and 18 as 2 times 9. And now using this we get our final answer that cokernel of psi is isomorphic to the product of z3, z4, z, z2 and z9. This completes the solution of problem 2. Problem 3. Determine the number of elements of order 4 in the group Z5 times Z10 times Z20 times Z30. Solution. An element A, B, C, D in this group, so A is in Z5, B in Z10, C is in Z20 and D is in Z30. So an element A, B, C, D in this group has order 4 if and only if the following conditions are satisfied. A should have order 1, 2 or 4 in Z5. B should have order 1, 2 or 4 in Z10. C should have order 1, 2 or 4 in Z20. D should have order 1, 2 or 4 in Z30. And at least one of these 4 elements should have order 4. Since 5 is an odd number, Z5 has no elements of order 2 or 4. by Lagrange theorem, and therefore A must be equal to the class of 0. A is the identity element of Z5. There is no choice for A. So in Z10, 10 is divisible by 2, but it's not divisible by 4. So Z10 has no elements of order 4. It has a unique element of order 1, which is the identity, the class of 0, and it has a unique element of order 2, which is the class of 5. So B can be either 0 or 5. 20 is divisible by 4, and 20 divided by 4 is 5, so that 20 has 4 elements of order which is divisible by 4. So we have the identity element 0, which has order 1. We have the class of 10, this is 2 times 5, it has order 2. And we have the classes of 5 and 15, these two elements have order 4. Finally, 30 is divisible by 2 but not by 4, so that 30 has no elements of order 4, and so our last element D can be either 0, that's the identity element in that 30, it has order 1, or it can be the class of 15, that's 30 divided by 2, this element has order 2. Since our choices are independent, putting everything together, we have 1 times 2 times 4 times 2 elements of order 1, 2, or 4. So we can choose A in one way, B in 2 ways, C in 4 ways, and D in 2 ways. Similarly, if we forget the choices for C as 5 or 15, we have 1 times 2 times 2 times 2 elements of order 1 or 2. So we have 16 elements of order 1, 2, or 4, and 8 elements of order 1 or 2. If we subtract, the outcome is 8 elements of order 4. And this completes problem 3. Problem 4. Determine whether the group Z90 times Z60 and the group Z15 times Z30 times Z12 are isomorphic or not. Solution. In both cases, the easiest way is to reduce both groups to the decomposition given by the classification theorem of finite groups, and then compare those decompositions. For this, we need to decompose the corresponding indices into the products of powers of prime numbers. So 90 is 9 times 2 times 5, and so Z90 is Z9 times Z2 times Z5. Next, 60 is 3 times 4 times 5, and so Z60 is Z3 times Z4 times Z5. So this means that Z90 times Z60 has the following decomposition. Z9 times Z2 times Z5 comes from here, times Z3 times Z4 times Z5 comes from here. For the second group, 15 is 3 times 5, and so Z15 is Z3 times Z5. 30 is 3 times 2 times 5, and so Z30 is Z3 times Z2 times Z5. And finally, 12 is 3 times 4, and so Z12 is Z3 times Z4. This means that the product of Z15, Z30, and Z12 decomposes as Z3 times Z5 times Z3 times Z2 times Z5 times Z3 times Z4. And if we compare these two decompositions, so the indices in the first decomposition are 9, 2, 5, 3, 4, 5, and in the second decomposition the indices are 3, 5, 3, 2, 5, 3, 4. So we see the index 9 in the first decomposition and it doesn't exist in the second. So this implies that these two groups are not isomorphic. And the fact that we have 9 in the first decomposition and no 9 in the second actually means that the group Z90 times Z60 has elements of order 9, while the group Z15 times Z30 times Z12 does not have any elements of order 9, so they cannot be isomorphic. And this group doesn't have any elements of order 9 because 9 is a power of a prime number, but no factor here is divisible by 9. And this completes problem 4. Problem 5. Determine all Sylow P subgroups of the symmetric group S5 for all P. Solution. The cardinality of S5 is 5 factorial, which is 120, and the prime power decomposition of 120 is 5 times 3 times 2 to the power 3. So we have CIL of 5 subgroups, CIL of 3 subgroups, and CIL of 2 subgroups. Let us start with CIL of 5 subgroups. Each such subgroup has order 5, because we have only 5 in this decomposition, and hence is generated by an element of order 5. In fact, it's isomorphic to Z5 because 5 is a prime number. An element of order 5 in S5 is just a 5 cycle. And the group S5 has 5 factorial divided by 5, 24 5 cycles. Each group of order 5, so Z5, has 4 elements of order 5 and is generated by any of these elements. So as soon as we have one of these elements, we have the 3 other elements automatically. We have 24 elements of order 5. Each subgroup of order 5 has 4 of them, so we should have 24 divided by 4, 6 subgroups of order 5 in S5. And we can list them. So these are the subgroups. The first one consists of the identity, then we have the 5 cycle 1, 2, 3, 4, 5, and its powers. The second subgroup has the identity and the 5 cycle 1, 2, 4, 3, 5, and its powers. Then we have identity 1, 3, 2, 4, 5, and its powers. Then identity 1, 2, 3, 5, 4, and its powers. Then the identity 1, 4, 3, 2, 5, and its powers. And finally the identity 1, 2, 5, 4, 3, and its powers. So we have 6 CIL of 5 subgroups. Note that 6 is congruent 1 modulo 5, and also 6 divides 120 divided by 5. So we are done with CIL of 5 subgroups. Let us now go to CIL of 3 subgroups. Each CIL of 3 subgroup has order 3, because 3 divides 120 and 9 doesn't, and hence it is generated by an element of order 3. So it's each subgroup with 3 elements is isomorphic to Z3, it's generated by an element of order 3, and an element of order 3 in S5 is just a 3 cycle. The group S5 has 5 choose 3 times 2, so we choose the support of the 3 cycle, and then for each support we have 2 3 cycles. So we have 20 3 cycles in S5. And each subgroup of order 3 has 2 elements of order 3, is generated by any of them. So we have 20 elements, 2 per subgroup. This means that we have 10 different subgroups of order 3 in S5. So we have 10 CIL of 3 subgroups in S5. So these are the following subgroups. We can take the identity and then the 3 cycles on 1 to 3, the identity and the 3 cycles on 1 to 4, the identity and the 3 cycles on 1 to 5, the identity, the 3 cycles on 1, 3, 4, the identity, the 3 cycles on 1, 3, 5, the identity and the 3 cycles on 1, 4, 5, the identity and the 3 cycles on 2, 3, 4, the identity and the 3 cycles on 2, 3, 5, the identity, the 3 cycles on 2, 4, 5, and finally the identity and the 3 cycles on 3, 4, and 5. And of course, 10, the number of subgroups, is congruent 1 modulo 3, and also 10 divides 120 divided by 3. So we are done with CIL of 3 subgroups, and finally let us do CIL of 2 subgroups. So the maximal power of 2, which divides 120, is 8, so it's 2 to the power 3. So we need to determine all subgroups of S5 which have 8 elements. Recall that during the lecture we actually computed all CIL of 2 subgroups of S4, and those also had 8 elements because S4 has 24 elements and 24 is divisible by 8. So we know 8 element subgroups of S4, and S4 is a subgroup of S5. So we can embed S4 into S5 by taking an element in S4 and saying that it acts as the identity on the element 5. And so any 8-element subgroup of S4 is automatically an 8-element subgroup of S5. So any CIL of 2 subgroup of S4 is also a Sylow 2 subgroup of S5. And we computed that S4 had 3 Sylow 2 subgroups. We will list them shortly, but now we can say that the set 1, 2, 3, 4, 5 has 5 4-element subsets. So we can embed S4 into S5, roughly speaking, in 5 different ways. So this means that S5 will have 5 times 3, which is 15 Sylow 2 subgroups. And note that 15 is congruent 1 modulo 2, and also 15 divides 120 divided by 8. Actually, 15 equals 120 divided by 8. So the subgroups which we had in the case of S4 are the following 3 subgroups. The first one consists of the identity, then the 4 cycles 1, 2, 3, 4, its inverse 1, 4, 3, 2, the transpositions 1, 3, and 2, 4, and the products of commuting transpositions 1, 3, 2, 4, 1, 2, 3, 4, and 1, 4, 2, 3. The next subgroup contains the identity, the 4 cycles 1, 2, 4, 3, and 1, 3, 4, 2, the transpositions 1, 4, and 2, 3, and the 3 products of commuting transpositions. And the last one has the identity 1, 3, 2, 4, 1, 4, 2, 3, the transpositions 1, 2, and 3, 4, and the 3 products of 2 commuting transpositions. So this is taken from our lecture, and now this is for the subset 1, 2, 3, and 4, and now we can take these 3 subgroups for all other 4-element subsets of 1, 2, 3, 4, 5. So we should substitute 1 or 2 or 3 or 4 by 5. So in this way we obtain the following 12 additional subgroups. So first of all, we have the 3 subgroups which we get when we substitute 4 by 5 in our list. So we have the identity 1, 2, 3, 5, 1, 5, 3, 2, 1, 3, 2, 5, and the products of commuting transpositions 1, 3 times 2, 5, 1, 2 times 3, 5, and 1, 5 times 2, 3. And similarly for the 2 other subgroups. And then we take the 3 subgroups which are obtained from the previous list by changing 3 into 5. And then we can change 2 into 5. And then we can change 1 into 5. And then we get all other subgroups. And that's a complete list of all Sylow 2 subgroups in S5. This completes problem 5. Problem 6. Prove that any group of order 44 is solvable. Of course, one way to solve this problem is to try to classify all groups of order 44, but that's actually sounds quite hard. So let us try to do it in some theoretic way. So let G be a group of order 44. The only thing which we know about G is that it has 44 elements. In order to prove that it is solvable, we need to find some subnormal series in G with abelian subquotients. So for this we need to find some normal subgroups of G. What do we know about possible subgroups of G? The only possible subgroups of G which we know exist are essentially Sylow P subgroups. 44, the order of 4, is 4 times 11, so it's 2 squared times 11. So we have Sylow 2 subgroups with 4 elements and Sylow 11 subgroups with 11 elements. So let us consider Sylow 11 subgroups in our group G. The question is, how many Sylow 11 subgroups do we have in G? What we know about the number of Sylow 11 subgroups in G? We know that this number divides 44 divided by 11. So this is 4. So the number of Sylow 11 subgroups in G should be 1, 2, or 4. At the same time, we also know that this number is congruent to 1 modulo 11. 2 and 4, they are not congruent to 1 modulo 11. So this means that there is a unique Sylow 11 subgroup of G. Let's call this subgroup H. Since it's a unique subgroup of order 11, it must be normal. Since H has 11 elements and 11 is a prime number, H is isomorphic to Z11, and this is an abelian group. So now we have inside G, we don't know what G is, but we know that G contains a normal abelian subgroup which is isomorphic to Z11. The quotient of G modulo this subgroup H has order 4, and finally we claim that any group of order 4 is abelian. Indeed, let K be a group of order 4. If K has an element of order 4, then of course it's isomorphic to Z4, and this is an abelian group. So assume that K has no elements of order 4, and then of course all non-identity elements of K must have order 2 by Lagrange theorem. So let these elements be A, B, and C. What can we say about the product of A and B? Since A squared is equal to the identity, AB cannot be equal to the identity, so B cannot be equal to A, because the inverse is unique. Similarly, if AB is equal to A, we multiply with A inverse. This implies B is equal to the identity. Contradiction. So AB is equal to A is not possible, and similarly AB is equal to B is not possible. So the only possibility is that the product of A and B is equal to C. And by the same argument, the only possibility for the product of B and A is that this product is equal to C. But then AB is equal to BA. So A and B are two commuting elements and they generate K. And so K is a commutative group. Therefore, identity inside H, inside G, is a subnormal series with abelian subquotients. H is abelian and the quotient of G modulo H is abelian. And this shows that G is indeed a solvable group. Some additional problems and questions at the end. Problem question 1. Find a presentation for the symmetric group S4. Problem question 2. Determine the number of elements of order 6 in the group Z4 times Z9 times Z36 times Z24. Problem question 3. Determine a decomposition into a product of cyclic groups for the cokernel of the endomorphism of Z3 given by the matrix 6, 6, 6, 6, 8, 6, 6, 8, 32. Problem question 4. Determine all Sylow P subgroups of the group A5 of all even permutations inside S5 for all P. And problem question 5. Prove that any group of order 12 is solvable. Thank you very much and see you next time.